Hello out there, and a warm welcome to this last morning session within the world of electrification and automation. My name is Michaela Münnikes, and I will gladly guide you also through this presentation. Our next speaker is not what you expect, because I think when you dial in, there was mentioned Klaus Wagner, and due to personal reasons, Klaus is not with us in the studio today, but my dear colleague Sebastian Schneider
hello.
Agreed to jump in and take over Klaus' presentation on effective motor protection solutions. Sebastian, thanks for jumping in. And nevertheless, please feel free to post your questions during Sebastian's presentation. We will try to answer them live at the end of the presentation. I think you will understand that it might be that Sebastian has one or two questions where he will not be able to answer, but no problem. We will answer questions via mail afterwards by our dedicated specialists. So I'll try to address your questions to Sebastian. Make intensive use of this possibility to address our experts. We are here just for you. And yes, we do record the session, and yes, you will get access to the recording afterwards. Sebastian, you're here to focus on effective motor protection solutions, and the auditorium is hopefully curious to learn about the benefits of SIPROTEC-5 devices, and therefore, the stage is yours.
Thank you very much. Hello, and welcome to this presentation about motor protection. My name is Sebastian Schneider. I'm the Product Lifecycle Manager for Transformer and Generator Protection, and today I would like to show you which faults and problems could happen with motors and how we can solve these with a SIPROTEC-5 device. Before we go into details, let me present our SIPROTEC-5 devices which provide a motor protection for you. The smallest of our classical devices is the 7SK82 device, which contains all necessary basic functions for protection of inductive motor or asynchronous motors. For the non-modular series, the hardware setup is limited to 4 CT sets and 4 VT sets, so that the differential protection is unfortunately not possible with this device. The modular 7SK85 is the expandable counterpart of the 7SK82. Here, for example, beside the further binary inputs, also another CT sets can be added, which allows you to perform also differential protection with this device. The next one is the 7UM, and these have the full scope of protection functions for generator, motor, and transformer as well. For this device, for example, under-excitation and rotor ground protection is provided and available in the library. The next one is the newest one in our SIPROTEC-5 family. This is the 7SX800. This belongs to the new SIPROTEC-5 compact class. The X in the name indicates that the device is not limited to a certain protection purpose, but unleashes possible several protection families into one hardware platform. For example, also motor protection as well. And last but not least, I would like to mention here as well the 7SX85, which is a modular device. And this is our universal device on the classical hardware platform. This device can take over the functionality for different SIPROTEC-5 devices. In that way, it could be also used instead of the 7UM, depending on the motor type, instead of the 7SK85. So, come we to the type of faults and problems. Let us now have a deeper look into the typical types of faults and problems. I don't want to present all this table in detail, so you can download later the slides for further studies if you like. I would rather focus on the left column to give an overview of the most of the most important problems. First, we have a short circuit, and this can be a three-phase or a two-phase faults in grounded networks, and also a single-phase faults in isolated or compensated networks as well. In isolated or compensated networks, single-phase to ground faults do not cause a short circuit, but rather a limited current coming from the capacitance. For this kind of faults, we provide our standard so-called sensitive ground fault protection functions, which are often required to be a directional element. Motor starter can be overheated when the load current is higher than the permitted current, which have a longer time, and the rotor is especially thermically stressed during a startup, or even worse, when the rotor is blocked completely. Then we have some functions that is also protected: a driven load, detection of unloaded drives like pumps, which could get damage without load, a protection against load jam to protect bearings and gearing. Finally, for synchro motors, 7UM and 7SX85 provide under-excitation functionality against loss of field and asynchronous operation. Let's have a look on the overcurrent protection. The most used short circuit protection, it requires a measurement of three-phase currents. It's a quite simple and cheap protection principle on the one hand. However, it has a disadvantage. The currents only above or over the startup current or load current can be detected. Short circuit protection, for example, is more sophisticated, the principle of the differential protection. It can detect faults which are much below the load current, and also during the startup of the phase of the motor, and so guaranteed to detect fault currents before they're evolving to a big currents with a higher destructive potential. This method, however, needs to be measured three-phase currents also behind the starter windings, which is on the neutral point of the motor, which required an additional CT set on the primary side and another CT inputs on the protection device. Therefore, we have to use a modular device. A variant of the differential protection is to use the three window type CTs, each for one phase, and bring back the cable to each phase separately so that the current upstream and behind the motor is compensated magnetically in this CT. The differential current is formed in the CT, and the resulting measurement on the secondary side is a current which is around zero. So we have finally on the secondary side of the CTs a Kirchhoff. Of course, this application needs a second CT set for all other protection functions like thermal overload protection or standard overcurrent protection as well. So here is the starter current curve for a motor that starts, and the continuous run under normal condition. We see truly short transient peak about the 50 milliseconds, followed by relative constant, however, slightly decreasing current on the motor speed. Sorry. Shortly before the motor reached the normal operation condition, the starter current drops down to the normal current, or depending on the load, to any other operation state. Following this curve, we can apply a short circuit protection. An underlaid overcurrent stage must be set over the transient starting current, which is often around twice a long-term starting current. A safety margin of 30% is a practical and also true RMS measurement to work against possible CT saturation, where the true RMS is less influent. A second stage above the starting current needs delay time so that this stage do not trip due to the transient starting current. The exact time can be measured during the commissioning. This stage can be set, for example, to a value of 100% of the starting current. Measurement of the fundamental can be set in order to filter out the DC components, which would be more considering the true RMS measurement. The third overcurrent stage could be applied just above the normal current to increase the sensitivity for short circuit current detection. However, delay time must be well above the maximum. Possible startup time, and it is so depends on this time if such a stage is really useful. Better is a differential protection which allows us to detect small currents with an additional stabilization methods against CT saturation. These methods cost, of course, some milliseconds time delay. Therefore, we use a fast differential stage which have to be set over the starting current. However, without the differential protection, the load jump protection can increase the sensitivity and the speed of an overcurrent protection. This is blocked during the motor startup, activated only when the motor is running, so it can be set lower than the starting current. However, should not be so sensitive so that the normal jumps do not trigger the states after it and the transient currents. The current motor feeds into an external fault, does not trip the motor. Also, voltage dip with a slightly higher stator current, when the voltage recovers and the motor speeds up, can be compensated by such a delay. So you see that a delay time for overcurrent functionality is important to be assured that the device is not tripping during normal conditions like motor start. The starter can be overloaded. Of course, the starter can be overloaded if the motor is too high for a longer time. This happens, for example, when the motor voltage is below the nominal voltage, or for a longer time, the load is too high in that case. A simple approach to monitor the starter overload is use an inverse overtime current curve. The SIPROTEC relays, more than 30 years, use a temperature calculation based on so-called thermal single-body model, as shown in the below, considering of the power source. On the left terminal, the capacitance which heats up by one of part of this power, and on the thermal resistance, we dissipated the other part of this power. Motor manufacturers do not deliver this parameter, but a clever simplification of this model can be used to monitor permanently the stator temperature and use the data which is available by the motor manufacturers. Oh, sorry, please stop. I was a little bit too fast. So, heating or cooling down from one temperature level to the other temperature level is shown in the diagram as θ1 and θ2. With the constant current flows, an E function is shown in the picture on the right with the full formula considering the preload condition, of course, with the temperature of θ1. And the ambient temperature, θu, on the far on the right of the equation. The second parameter is described in the stator temperature and give the, oh, I was too fast. The second parameter, this is so-called the key factor, where the key times in the nominal current is the maximum permanently permissible current of the machine. This factor normally is around 1.1 or 1.2. That means 110 or 102% of the nominal voltage. The second parameter is the terminal time constant tau, which describes how fast the motor heats up to the new end temperature. Typical values here are between 10 and 30 minutes for a motor. For permanently fluctuation currents, they really increase these in a way that the temperature follows accordingly. This model guarantees a permanent supervision of the stator temperature. Next slide. The next slide is related to the restart inhibit function. The rotor is extremely sensitive during a startup because the starter currents in this period are relatively high. Therefore, we have two protection functions, the restart inhibit function, and later discuss the starting time supervision. The restart inhibit function monitors not too many starts happen in a certain time, that the rotor has a time for cooling down and is not overheated. In some cases, the given motor data describe a simple approach, like a certain number of starts, a certain number of time, for example, 3 starts in 1 hour. How these starts are distributed is not specified. Or a certain maximum time must be guaranteed between 2 ongoing starts. Our restart inhibit function has some specific stage which works on these principles. However, we built in also a terminal model to describe a rotor temperature stress more precisely, providing a higher flexibility in use of the motor. This terminal model is based on the number of starts from the cold and the warm states. Additionally, the starting current and the time is required for which these two numbers are guaranteed by the motor manufacturers. This often not only the starts under normal condition with full voltage, but also for a longer startup with a reduced voltage will stress the rotor much more. To give you a feeling, we show you a temperature curve when the rotor does not start to move at all. We see that the end temperature of the blue curve is far above the maximum permissible temperature. The red line is which is the terminal limit where the theta max equal 1. In our calculation example has a value of 8.6 times of the maximum allowed temperature. Whereas the temperature under normal conditions, theta n, is around 34%. In the diagram shows why the too long starts in a row overheats the rotor strongly. The required settings for this function are the number of cold starts and warm starts, which allows for the certain startups current and startup times, as you can see on the slides below. And to remember, the rotor temperature is calculated permanently from the device. So come we to the next functionality, the restart inhibit. Here we see the rotor temperature for 3 ongoing starts with a short running period. The temperature is not equal disturbed in the rotor bars, which is indicated by the red and blue colors. However, we calculate an average temperature which is allowed by the fact that the given motor data allows a certain number of starts, without considering any special location of the rotor. We see the restart limit or the restart inhibit threshold, which is the temperature value from the exactly one and the other starts possible to reach the maximum rotor temperature, which is 1. The function as such does not trip during a motor start, but prevents in that way that a motor starts under standard condition does not exceed the maximum of a temperature. The restart inhibit signal, marked in a red button, is activated when the threshold is exceeded and the motor is at standstill or running down additionally for set the belt short time for each stop. The rotor bars balancing out that the close command for a SIPROTEC-5 device is automatically blocked in such a case. To block an external close command, this signal is available in the routing matrix and can be routed on the binary output. Next slide. So different to the restart inhibit function, the motor supervision monitors a too long startup of the monitor, of course. The motor data usually make a difference for the startup from a cold to a warm start. In the motor diagram, we can see 2 curves the blue for the cold one and the red for the warm start, for the maximum locked rotor time. These curves are given in the right part of the diagram. If the locked rotor time is longer than the maximum expected start time, this time can be used simply because during the startup of a rotor, during the startup of the motor, the rotor is moving and being too cooled, and the startup current is decreasing. If the motor or if the rotor is locked in that time, then we can react faster, and we have a standard startup time. A speed meter must be installed to trip earlier in that case, and this signal can be registered by the binary input, which leads to an accelerated trip of the SIPROTEC-5 device. Either the motor data is given with values from the starting current and the corresponding maximum locked rotor time, or one can get a couple of these values in the curve on the left-hand side. The protection function is based on the simple E²2 time inverse function, which is started by the motor current exceeding and the starting threshold. The starting current and the corresponding starting time describe this curve. We are often curves for starts for cold and for another starts on the warm side. In the given example, we read out that the motor starting of 84 seconds for a starting current of 5 times nominal current, which enters as a setting for your startup, the supervision curve. A slightly lower value for the maximum times give us some reason, considering that the startups and this time of this motor is just 12 seconds, so far below the maximum startup time. Finally, I would like to talk a negative sequence current, unbalanced load protection. The rotor is very sensitive for negative sequence current, and this had to do with the fact that these currents are rotated in a counter direction to the rotor cage. And this heats up the rotor intensively and needs to be monitored by the device. Negative sequence current come from the voltage unbalanced on the motor terminals, or if one phase is open, for example. To model this terminal stress for the rotor, a simple thermal model on an E²2 curve is used in that case. Similar to the starting time supervision, the function is triggered when the measured negative sequence exceeds a permanent permission value. This often is around 10% of the nominal voltage and shown as 0.1 in the tripping characteristic to model the heating value of the E²2 to the nominal voltage. And corresponding maximum allowed time is given by the motor as a motor data. Often this is the time where the E²2 is equal En, the nominal voltage. This time is named as K, which is not to be mixed up with the K factor for the starter overload protection. The values lies in the range of a couple of seconds. Alternative, a diagram is provided as motor data from which these values can be derived. In the example, we have the maximum time on the x-axis and the corresponding negative current on the y-axis. If we search here for 1, that means the negative sequence current is equal to the nominal current. We find the corresponding time, and this is 50 milliseconds. This value for the key is used for the parameter key. So come we to the summarize of my presentation. This was a brief overview of some motor protection functions in our SIPROTEC-5 device. We talk about the overcurrent and differential protection as short circuit protection. Came across the data overload function and the terminal model, and we discussed the SIPROTEC-5 device offered an additionally and sophisticated terminal model for the rotor, which is the basis for the restart inhibit function using as model. using this model, and the function allows much more flexible operation of the motor, monitoring at the same time permanently the rotor temperature. We saw to set the starting time supervision based on the lock rotor times, and finally I gave you an insight into the unbalanced load protection, which is based on the terminal model for negative sequence current. Our motor protection device offers an additional function to protect the driven load, for example, load jump protection against sudden hidden loads, or undercurrent protection to protect pumps against dry running, for example. If you would like to have more in detail information about the motor protection application, we are about to publish to read some motor application guides where we have the link, I think, on the in ZEOS, and together with the manuals of the motor protection, you can see that. I hope you enjoyed this presentation and found it useful. And now we have some time for some questions. Thank you.
Thank you, Sebastian, for jumping in. That was quite a comprehensive presentation, so we are almost running out of time for questions live here, but you still have the chance to talk to the experts within the exhibition area of this world of electrification and automation. And if you push there, this red button, contact the expert, you can meet them directly into Teams. But there we go, there's this button. So if you want to talk to somebody, just push the button there. The experts are there for you. Sebastian, not right now because he's here in the studio with me, but we have definitely more experts on SIPROTEC-5 and its solutions. And we take one question from the auditorium, and we'll see if you can answer it or if we will answer it afterwards.
I will try it, of course.
You will try. MP wants to know, is artificial intelligence included in these modules so that it would check what are the characteristics of the motor and adjust the settings as needed?
Very good question. So this question comes very often. So no, not yet. But we work on such a topic. So it's more and more coming from the market that this kind of requirement should be implemented, because normally the customer do not have all these data. Yeah, and of course, motor protection is very complex. So yes. And to get all this data and understand this data is not quite easy. So we need a long time to do all the settings. So of course we have to go in that direction to more to give the customer more a guideline how to set it, to read it out if possible from the motor, of course, and to use especially all these given motor data that you can find on the nameplate of the motor. But this is a good point, and I will take it with me, of course. And I think it is a step in the right direction to be more on a how can I say, on a simple way to parameterize motor protection.
Cool. Great to learn that we already talk about, or at least think about, artificial intelligence there. I didn't dare to imagine that we are that far at least thinking about it. And yes, I saw it's quite complicated. I think I remember all of this motor stuff somewhere during my study time, and yeah, must be hidden somewhere. That's okay. It's so great to see that you know what you're talking about there. So thanks, dear auditorium, for all your questions. We will take them with us. You will receive an answer. So via mail or later on in the expert chat, or get in contact with us. A lot of my colleagues are available via LinkedIn. You can contact us on our pages. I think we have one, siemens.com/SIPROTEC, and there you can contact us. We will get back to you soon. And the access to the recording is automatically available to all the participants. We prefer that we send the recording to you because we put a lot of effort in the text that you hear with us, so it's not the plain presentation you receive. If you just need the presentation, just give us a hint there. Thank you, Sebastian, once again for jumping in on this topic. Thank you out there for joining in and listening to us. Now we have some time to stroll around through the exhibition and meet the experts there, because here in the studio, in about 2.5 hours, our next conference speaker will then be my colleague Jorge Diaz with a precisely tailored substation automation with our product CCAM A8000. So please fill your personal agenda within the world of electrification and automation. Go to your Global Summit profile, select your desired topics from our offerings, and prepare your agenda. I already mentioned that between the conference lectures or now between the pause, you are invited to visit the exhibition area. We have curated content there from our specialists. You find, I think you already watched a bit of it, you find information on energy automation solutions, about medium and low voltage systems, and we also have their support and service information. We have receptionists there to guide you to our experts, so you don't have to know who's the expert for which portfolio, but we have receptionists there to guide you to our one-to-one meetings with the experts. So for now, thank you, Sebastian. Thank you for your time. Take care, enjoy the exhibition area, and see you later. Goodbye.
Bye.